3. Any questions on chapter 3 before we get started? All right, we will move on to chapter 3. Can you guys hear me?
Yeah.
All right, perfect.
Yeah.
Chapter 3, physical and chemical change. Again, like I said, we're going to cover chapters 1, 2, 3, and 4 rather quickly, kind of getting us through some basic information, but then we'll move on to some of the more fun stuff in relation to fire. So physical and chemical change. Some of our objectives name the 3 basic states of matter found in the material world and explain how they're characterized. We describe the phase change among these states and the change in enthalpy associated with each. We're going to talk about some ideal gas laws. We're not going to worry about writing or using these laws. I shouldn't say using, but writing them out. We're not going to balance chemical equations. You're going to find throughout this book that they deal with some different equations and things like that. We will not be focusing on that. We're kind of more intrigued by and going to focus on the concepts, not necessarily the actual calculations of some of these formulas that they present. Understand the meaning of fuel lean, stoichiometric, and fuel-rich combustion. Some of these terms you're going to see throughout the rest of the semester as well as throughout your career in the fire service. So it's going to be some good things, some of these key terms that we talk about through these classes to put to memory and learn what they are. Explain why the outcome of a combustion reaction is determined by thermodynamics. The rate of reaction is determined by chemical kinetics. Okay, and then describe the ideal and realistic flame temperatures. So as we look at way back in the 17th century, if you guys get a chance, as you read through the book, the introductions are very good. They give you some good things to think about and some stuff like that. So I'd make sure and pay careful attention to those as well. But in the 17th century, they had a theory. So 17th century would actually be the 1600s, that there's the theory that things burned contained phlogiston that moved from fuel to air. So as science developed and we were able to run more tests, learn more things, we know that oxygen from the air reacts with the fuel. So they were kind of along the right path with this, but it wasn't quite fully figured out. But you know that we know that oxygen is one of the things that we need to react from the air with the fuel in order for combustion or burning to take place. So we talk about states of matter. There are 3 phases or states of matter, and they are gases, liquids, and solids. So these phases can all be characterized by things such as sight, smell, touch, and your mobility. As you turn to page 29 in your book, one of the things in that second paragraph that you'll want to know and understand, it starts out with chlorine gas is an uncommon in that it is both visible and odorous. It appears green and the human nose is sensitive to it. So that's one of the things. I mean, many of you may notice that some liquids have no scent at all. Other liquids such as gasoline or chlorine or other types of things, coffee, have a scent to them, so you can smell them. So as we look at gases, they're sometimes odorless and colorless, but other times we know that they may have an odor, they may have a color. Their molecules are very mobile. So gases are usually at a higher temperature than their solid or liquid phases. And so they're moving around all over the place. All those atoms and molecules within that body are moving around. They spontaneously expand and mix with other gases, and they expand and contract in proportion to the pressure and temperature changes. So as the temperature cools down, the gas begins to contract. As it heats up, the temperature heats up, the gases begin to expand and become more, they move a lot more. So a vapor is a gas that readily condenses to a liquid. So one of the things you may use is, say you're boiling a pot of water. Now, if you put a lid on top of that pot, what are you going to see build up on the inside of that lid? You're going to see that gas that's boiled up. It's hit the cooler lid and it's started to condense again. So that's turning back into a liquid because it's cooled off. As we talk about liquids, liquids have various colors. Our noses are sensitive to some liquid vapors and others they are not. Liquids are less mobile than gases. The amount is described by a volume, much as a volume of a gas. A liquid is also described by its volume, whether that's a liter of air or a liter of cola, liter of cola, or a liter of a liquid. It can disperse into other liquids, but sometimes this takes time. Then we move into the third phase, which is solid. Nearly are all colored. Nearly all solids are colored. Their vapors are usually odorless as they are more dilute, meaning that the concentration of vapor is not coming off as much as it is in a liquid or a gas for the same substance. Solids resist pressure when pushed, so most solids are very difficult to change their shape or that type of thing. And solids in and of themselves do not mix with each other just by themselves. As we look at, we see that many substances are a combination of more than one state of matter. I'm going to stop sharing my screen here a second. So I have a glass of water that I used to drink with. We know that to be a liquid state. If you look in this cup, I filled this cup up just before. Let me dump some of it out. As you guys can see, that there's some ice that was in there, which is a solid water. But we see that those changes between those states, whether it's a solid, liquid, or gas, happens for various reasons. And we'll look at that here in just a bit. Oops. So gases, their individual atoms or molecules moving in random directions at high velocities. We talk about atmospheric pressure. At this temperature and pressure, we see that most gases move at a velocity of about 460 meters per second. They collide with each other and change directions about 10 billion times per second. So these gases in their volume are moving around constantly. Talk about the ideal gas law in 3 equivalent forms. So these are some of the ideal gas laws, and we can make some determinations and find some things out because of these 3 gas laws. So we look at some of the different things that are involved in the ideal gas laws. It deals with density, it deals with the mass, it deals with the atomic molecular mass, the number of moles, which is basically the number of, say, hydrogen particles that are in that total volume, absolute pressure, some of these other things. Air is the most important gas in fires. As we look at our normal air around us, it's the primary composition is made up of nitrogen and oxygen. So we see that for every 100 molecules of dry air, 21 of those molecules are oxygen and 79 of them are nitrogen. We find so that totals of about 100%. There's a few other things that are out there, but primarily our air is made up of nitrogen, 21% is made up of oxygen. Expressing a gas mixture in terms of mass fractions. This is, again, we look at oxygen. The mass of the molecular oxygen is 32. Its atomic mass of oxygen is 16. The reason it's 32 is because that oxygen molecule is diatomic, meaning there's 2 oxygen molecules bound together. So liquids, gas condenses into a liquid if the temperature is reduced. So how do we make a gas into a liquid? We lower the temperature. That temperature is reduced and it begins to go from the gaseous state to the liquid state. We can also move it into a liquid by the pressure being increased. This forces the molecules closer together. The molecules touch, they move relative to each other. As we talk about vapor pressure of a liquid, this is the pressure of gaseous molecules of the liquid at the equilibrium. So we're right at that point. Again, if you have, say, like a cup of water and we're heating it up, those molecules are starting to move around as they are able to break free or as they condense down. We look at some of those things, the pressure of those gaseous molecules, right at that equilibrium. And typically that equilibrium is right there at that top of that where it's being heated up and those molecules are moving from the liquid to the gaseous state. At the equilibrium, we see that the rate of evaporation, which is that liquid turning into a gas, equals the rate of condensation, which is the gas turning back into a liquid. We find the vapor pressure near zero at the freezing point. At the boiling point, the vapor pressure equals the atmospheric pressure. So we know that for water, for instance, the freezing point for water in Fahrenheit scale is 32 degrees. For the Celsius scale, it's 0 degrees. The boiling point for water in the Fahrenheit scale is 212 degrees Fahrenheit, and in centigrades, it's 100 degrees Celsius for water to boil. Talking about some of these measurements, again, we're not as concerned with what these measurements are. This deals with vapor pressures, depending on the type of substance it is, and depending on the temperature, that pressure can change. So changes in vapor pressure gradual at lower temperatures. They increase rapidly as the temperatures reach their boiling point. So the closer a liquid is to the boiling point, the more, the higher the pressure is going to be, because those molecules are escaping from that liquid. They're bursting out, they get a lot of energy, and they're moving into that gaseous state. So solids, liquids turn solid at a freezing point. Again, one of the most easiest things to use this is is water. We have water in a vapor state all around us. As it cools down, it turns into a liquid. As it cools down even more, it turns into a solid. And then we see that as we heat it up, so like I had shown you with the solid ice I had, it was turning into a liquid because it was being warmed. That solid was turning into a liquid. And if we were to continue to heat it up, that liquid would then turn into a gas. In dealing with crystalline solids, there's some different things that are happening. Atoms, ions, molecules are fixed in geometric positions or geometric shapes. They cannot move through solids. The heating of it causes vibration forces to exceed the forces holding them in place. Dealing with solids, liquids with large molecules do not form crystals when cooled. They become more viscous, molecules free to move. They eventually become solid, and molecules are trapped in random spots when solid. Metals are a special type of solid. They have positively charged atomic ions in a geometric crystal lattice. They have a matching number of electrons moving through the lattice. The high mobility of these electrons causes it to be easier to conduct heat and electricity. So this takes a metal such as like steel. We find that it conducts electricity as well as heat very readily because those electrons move freely from one molecule to the other. Some of the thermophysical steps. So thermo being heat related, physical means those phase changes, those changes from a solid liquid to a gas or liquid solid to a gas. Thermophysical steps when a solid is heated. So the temperature of the solid rises. The solid begins to melt, becomes a liquid. The temperature of a liquid rises. The liquid vaporizes or gasifies, and then the gas temperature continues to increase. Each step requires an influx of heat. So there may be chemicals from heat or chemicals that heat from the fire. As the room cools, the process reverses until matter resolidifies. So think about the same. As things cool, that heat is taken away from them, so that gas is turning back into a liquid, which then as it continues to cool, it turns into a solid. The process is same for fluid materials minus the solid phase step. So things that aren't going to necessarily turn into a solid, some of your more viscous types of things where we aren't going to see that as often because the temperatures don't get cold enough. They're just going to mainly change between that liquid and gas phase. Mm-hmm. So then you can calculate, how much heat is needed to change the temperature of a given mass. Again, we're not going to worry so much about that, but those are some of the variables that are factored in. The heat required deals with the mass, the heat capacity of the substance, as well as the temperature change. Heat capacity of common substances are listed right here. Transition between solid and liquid characterized by a heat of fusion. So the value numerically the same as heat of solidification, but it's in the melting, it absorbs heat, and in the freezing, it releases heat. There's a transition between liquid and gaseous states characterized by the heat of vaporization. This is numerically equal but opposite to the heat of condensation. So again, we're going from that liquid to gas where that heat, it's being vaporized, and then condensation, it's going from gas to liquid. Environmental pressures affect values of both heat of vaporization and the boiling points. Some solids vaporize directly without a liquid stage. This is known as sublimation. Sublimation is where it moves from a liquid or from a solid to the vapor stage without becoming a liquid in between. Direct change from vapor to solid, it can also occur. Water vapor changes to snow or frost. A carbon dioxide fire extinguisher. Expansion causes cooling, creating solid particles. With substance mixtures, transitions between state depends on the relative proportions of the substance, the temperature, and the pressure that's involved. Real combustibles almost always are assemblies of materials, meaning it's more than one thing. So such as carpet or upholstered furniture, there's more than one type of a thing in there. Chemical changes. So a chemical change is very different than a physical change. So fire is a type of combustion process. And what we see here is physical changes are accompanied by chemical changes. So what that means is a chemical change is it's creating a different product. Water, when it goes from solid to liquid to gas, it's still water. It's still two hydrogens, one oxygen. But when you add a fire to certain materials, and as it changes, a chemical reaction takes place, and we get something totally different. So burning molecules change into other molecules. Atoms combine in different ways with other atoms, and chemical bonds break and new ones form. There's a couple of types of combustion mixtures. So again, here, this combustion is dealing with fire type of stuff where combustion is taking place. The first one is called the stoichiometric mixture, and this is on page 36. This is going to be something you're going to want to know and understand. But a stoichiometric mixture is a mixture of fuel and oxygen exactly needed for complete combustion. So this means we have the right amount of fuel, we have the right amount of oxygen, and there's going to be complete combustion. As we look at another type of a mixture, we look at a fuel lean. So as the name implies, the original mixture for which the oxygen remains when all the fuel is consumed. So basically, we don't have enough fuel. We have plenty of oxygen, but not enough fuel when the mixture is fuel lean. Fuel rich means there's more of the fuel than there is of the oxygen. So the original mixture in which unburned fuel remains after the oxygen is fully consumed. So we would have some of that leftover fuel even though all the oxygen is gone and combustion has ceased. Combustion is usually incomplete in large fires. Usually there's a fuel rich in the most hazardous stages of fire. If insufficient oxygen for a complete reaction to take place, the final products we need to know is which combustion products are formed and how prevalent are they? Because a lot of these combustion products that remain are very harmful to us, especially as firefighters, as we go in there and take care of the fire, such as in the overhaul stage or something like that. One of the big things that comes out of that is carbon monoxide. We know that carbon monoxide is not good for our bodies to breathe. It does some things to our cells that blocks the oxygen from being transported, so it's not good. In a fire, there are hundreds of chemical reactions that take place. So some of the things that we look at is what chemical change is occurring. You know, if we know what kind of products there are, we might be able to make some determinations about that chemical change, what the results are going to be. How much enthalpy or energy does that change absorb or emit? You know, how much heat and stuff like that does it give off? And how fast are these chemical reactions going to take place? If we look at the process of oxidation, you know, we see that sometimes if we have something, oxidization is actually a part of combustion or whatever. It's a slow moving process. You know, we see that a metal will rust slowly over time, but we can also have another type of reaction that happens very, very quickly in just a millisecond. This is dealing with some chemical changes. Again, we're not going to be so concerned with the formulas and what's happening, but just know that when those chemical changes take place, we're getting different products than we had before. Some things about chemical changes: the higher the temperature, the more rapid the chemical reaction. And flames result from the gas phase chemical reaction sequence. So a liquid fuel must vaporize for it to burn. A solid fuel undergoes pyrolysis in order for it to burn, producing vapors that react with oxygen. So a gasoline in and of itself will not burn, but the vapor that it gives off when it vaporizes, that is what burns. And as it burns those vapors, it continues to heat up the liquid underneath and continues the process until either there's not enough oxygen or that liquid is completely vaporized and burned up. Now, solids, on the other hand, take like a piece of wood. The solid itself is not going to burn, but it takes a lot of heat. And what happens is that solid then pyrolyzes. It's that pyrolysis that takes place, and it produces vapors that then react with the oxygen in the air, causing it to burn. As that log continues to burn, continues to build heat, continues to pyrolyze and give off more heat vapors, and continues to burn until that log is either fully burned up or we run out of oxygen for the combustion process to take place. Oxidation, we talked a little bit about that. You know, propane burns by reacting with oxygen in the air. Oxidation takes place in fires, and it also takes place over time, you know, with certain materials such as metals, but that takes a much longer process. One of the things to remember is that atoms are neither created nor destroyed, but they change partners. So we aren't creating these or we aren't destroying them, but they're changing their makeup in that chemical process. As we balance some of these equations, so if we know what we have, what the makeup of a product is, we're going to be able to look at it and calculate how it burns and what it's going to create. And if we know how much of it we have, we know how much of the other products it's going to create as well. We'd also be able to tell, you know, what that maximum temperature that might be released, or how much heat it might give off, or how much volume of oxygen might be left after a certain amount of the fuel has burned. Again, these are not calculations you're going to be doing out in the field as you're, you know, pulling hose to put a fire out inside a room, but it's things to be aware of. Here's how they're going to balance the equations. So in summary, we look at the nature of chemical changes in fire is going to depend on the nature of the fuel as well as the equivalency ratio in the fire. Overall chemical change can be represented by a balanced chemical reaction. You need to know the elements to calculate how the chemical substances react with oxygen, the chemical formula of the combustibles, the air availability, and the combustion products expected to form. Chemical change is accompanied by a change in enthalpy, and it can manifest, that enthalpy can manifest as heat, electrical energy, or mechanical energy. Dealing with some chemical reactions. Things at a constant pressure, a reaction in the open takes place at 1 atmosphere of pressure. Reaction in a closed container is a different story though. This deals with the oxidation process. The heat freed by the reaction depends on whether the water after cooling is assumed to be a gas or liquid. In fires, cooling is slow, so water vapor condensation takes time. Most combustibles produce flames at temperatures from 2100 to 2300 Kelvin when just burned with the stoichiometric amount of air. This is under conditions where there is no heat loss. Chemical equilibrium is achieved rapidly in these conditions. Chemical kinetics, again, we talked about the rate of chemical reactions. So we talk about incomplete combustions. This is going to be one of the things that we're going to learn about later on in further chapters, but we look at things like tailpipe emissions, fire soot. These are some of the some products of combustion. Smoke is a product of incomplete combustion. So if you have a fire that's giving off a lot of smoke, you have incomplete combustion. So a lot of that smoke is made up of unburned fuel fuel that wasn't consumed. If you have a very clean fire that's burning most of the materials, you'll have very little smoke. A fire that's not burning too clean, it's not burning off all that material, is going to be a very smoky type fire. Moving on through some of these. So as we summarize, our world is composed of gases, liquids, and solids. These phases are characterized by sight, smell, touch, and mobility. Molecules move independently in a gas. Bulk properties of a gas are related by the ideal gas laws. Gas mixtures are described based on volume or mass. Molecules in liquids have limited mobility. Mixture of liquids happens more slowly than that of a gas. Liquid gasifies by vapor evaporation. Vapor pressure and vaporization rate of liquid increase with temperature, which is important in the ease of flammable fluid ignition. Solids pyrolyze when heated, generating gaseous fragments that are different from the solid's chemical structure, and that's actually what burns when a solid is burning. The heat needed to raise the temperature of a liquid or solid depends on the material's heat capacity and the temperature rise of the interest. The heat must be added to produce a phase change in order for it to burn. Fire is a combustion process. Products are grouped based on whether the combustion is fuel lean, meaning that there's not enough fuel, stoichiometric, meaning there's the right balance of fuel and oxygen in the air, or it's fuel rich, meaning there's more fuel than there is oxygen to be able to burn. Balancing the overall fuel-air reaction equation provides a tool for quantifying the enthalpy, the amount of energy that's generated by the combustion process. Chemical thermodynamics provide information about the combustion products. Chemical kinetics determine how quickly the combustion process proceeds and if there is time for the fuel-air mixture to reach equilibrium. Burning reactions increase exponentially with temperature. Heat released by the burning of an organic fuel per gram of oxygen consumed is nearly independent of the fuel's chemical structure. So flame temperature is a function of the fuel heat's combustion, the atmosphere's heat capacity, and the heat lost to the surroundings. So that is chapter 3. As we turn back to page 30 or 29, we're going to look at a few of the items that you may want to know and understand in preparation for the quiz. Under states of matter, characteristics of phases, we talked about chlorine gas. This is in that second paragraph. Chlorine gas is uncommon in that it is both visible and odorous. It appears green, and the human nose is sensitive to it. As we turn to page 31, you're going to want to know and understand vapor pressure. The vapor pressure of a liquid is the pressure of the gaseous molecules over the liquid at equilibrium. That is when the rate of evaporation is equal to the rate of condensation. Moving on to page 35. You're going to want to know what the heat, it's in that left-hand column about midway down. Heat of vaporization, know and understand that. Move right across the page to the second column. You're going to want to know what sublimation is. This is found there at the beginning. It is also possible for a solid to vaporize directly without any liquid forming. This is sublimation. Page 36, chemical changes down at the bottom. Know what a stoichiometric mixture is. On page 38, you're going to want to know and understand pyrolysis, endothermic reactions, and exothermic reactions. Endothermic reactions are reactions that take place where heat is absorbed. And an exo, meaning it gives off. So think of endo as taking in, exo is giving off. Exothermic reaction, these reactions release heat. Page 42. Just above where it says chemical equilibrium and chemical kinetics, that last sentence there, it says, consequently, the maximum flame temperature in a fire will be near 1500 Kelvin to 1600 Kelvin. Notice the K, the Kelvin. So that's going to be warmer than 1500 degrees centigrade or 1600 degrees centigrade. Chemical equilibrium, right under there, there's a sentence, the second sentence starting out, it says, at some point, In the time, the reactions would slow and then cease because the atoms in the box would have rearranged themselves into the most stable combinations possible at the prevailing temperature and pressure. So this chemical equilibrium is when all the chemicals that are reacting balance each other out and they're happy. So they've reached that chemical equilibrium. Any questions on chapter 3 thus far? I apologize. I was going to put the PowerPoints up there. I will work on getting those up there and available for you guys to go through and to review throughout the week as you prepare for your quiz. Again, I apologize for not having those done so previously. No questions? Then we will move on to chapter 4. Let me find what I need here. So we're going to talk about flow of fluids. Our objectives describe the basic laws of motion and gravitation. Again, we're not going to calculate pressures, not going to calculate the velocity, but we will describe potential and kinetic energy, as well as describe the effects of fluid viscosity and buoyancy on fire flows. Shoot me a message in chat. Has anyone heard of fire flows and flow paths, that type of a thing? Just shoot me a yes or no if you can. So some of the things as we look at, again, these introductions have a lot of information. Fires of note, Baltimore in 1904, there was a fire that was aided by the wind. And what they found is that 1/4 of the city was destroyed. More recently in 2013, there was a wildland fire involving the Yarnell Hills in Arizona. And with that fire, 19 firefighters died suddenly following a sudden change in direction of the wind. And in 1990, the MGM Las Vegas Grand Hotel, or the MGM Grand Hotel fire in Las Vegas took place. The fire never rose above the 2nd floor, but people died in rooms as high as the 25th floor because of the toxic smoke. Now, all of these fires had a devastation. And you're going to find that many of the fires we study and things that we learn from are because either one, people have died, or there's been a tremendous loss of property. But we learn a lot of things when these fires are studied. Oops. Sorry, I apologize. I believe I stopped the screen share. Oh, no, it's still there. Never mind. So what we're going to find is that these fires get studied, and in doing so, we learn some different things about these fires. As we talk about flow of fluids, now these fluids aren't necessarily always liquids. They may be gases as well, but as they move, these fluids flow. So fluid flow considerations, some things to think about is their access to water, airflow to fire and its transporting of smoke and other gases. Principles governing the movement of rigid ideal objects, so association with flow of fluids, fresh air into a fire. This is going to give the fire the oxygen that it needs to cause that combustion process to continue. Fire-driven airflow laden with combustion products is going to drive the fire into different areas, and flow from fire suppression systems, meaning such as water or fire retardant materials, is going to affect how that fire behaves as well. So at any given time, momentum, we're talking about momentum. At any given time, an object has momentum equal to its mass times its velocity. So if an object is at rest, its velocity is 0. So momentum, an object at rest tends to stay at rest, and an object in motion tends to stay in motion until other things act upon it. So we talk about Sir Isaac Newton's basic laws of physics. Again, last chapter we kind of talked about some chemistry type stuff. This chapter we're going to talk about more physics type stuff. If you guys don't have an understanding of chemistry and or physics, I would maybe suggest, doing some learning in those areas as well. So Newton's first law of motion: an object at rest or in motion tends to stay that way unless acted upon by an outside force. So momentum is conserved. A body in motion stays in motion unless an outside force acts upon it, which typically tends to be friction in our cases. The velocity remains constant until the object is perturbed or bothered or moved or something like that. The second law of motion: when a force or magnitude F acts on a body of mass M, the body accelerates in the direction of the applied force. So we can have an object accelerate in a certain direction. This may be gravity acting upon an object, or if we push an object one way or another, it's going to act and continue to move in that direction based on the amount of force that's enacted upon it. The third law of motion: every action is balanced by an opposite and equal reaction. So a good example of this for many of those of you who have used a fire hose: the force water going out of a fire hose is opposed by a backwards force on those holding the hose. So as you begin to open up the bail on a fire nozzle, you're going to get some force pushing back upon you. This is the nozzle reaction. This is Newton's third law of motion. So Newton's laws of universal gravitation: any two unchanged masses are attracted to each other by a force proportional to the two masses and to the inverse square of the distance between the two masses. So basically, how far apart these are and how much mass each of these determines how much they're going to be attracted to one another. Here's the equation for that. Again, if you can read that, you're better than I am. Objects near Earth's surface are 1 Earth radius from the center of the Earth. So as we get farther, we're farther away from the center of the Earth as we increase in elevation. Dealing with kinetic energy, mechanical work. The change in enthalpy or energy applies to both mechanical and thermal, being heat-related systems. Changes in energy and enthalpy are equal if a change in the mechanical system does not result in expansion or compression. So we're dealing with thermodynamics, thermo being heat-related. Energy is neither created nor destroyed. For example, the food energy used to ride a bike is balanced by the bike's mechanical movement and rider minus the energy to overcome wind resistance or the tire traction. So again, energy is not created nor destroyed, it's just changing its format. Energy that is stored and awaiting to be expended or used is known as potential energy. The difference in energy measured by mechanical work needed to achieve an aim. Okay, so you can imagine, potential energy is that stored energy. The force acting on an object in the gravitational field is g times the mass of the object. Okay, and it deals with the height as well. Kinetic energy is energy associated with motion. It deals with the force that acts upon a mass, which has been at rest. After the force, the mass moves at a certain velocity. If force is still applied, the mass accelerates. The object moves a distance, accelerating as it goes. If no other force on the mass, the kinetic energy to the object is the force times the distance. Here's some equations dealing with kinetic energy. Some basic elements of fluid and behavior. Force and pressure. Fluid change shape and dimensions during a physical and or chemical process. This pressure can be used instead of force, and density can be used instead of mass. So the pressure may vary from one region to another based on your altitude and some different things like that. Some things to think about. Gases are compressible, meaning we can pack them down. Think of an SCBA bottle. We take air from outside and we run it through an air compressor, and it compresses it down, and it stores a larger volume of air compressed down into a smaller volume of it, or a smaller oxygen or air pack. Density is the same everywhere for incompressible fluids such as water. Think about water, you can't compress it down. If you try and compress it, it's going to blow out of the container it's in. So going back, we look at things dealing with force and pressure. We look at a straw. When you use a straw to take a drink, you're decreasing that, or you're decreasing the pressure on the inside of that straw, and the external pressure is being increased, so it pushes that liquid up through the straw and into your mouth. So look at another type of fluid streaming from a hole in an otherwise closed volume. If fluid pressure inside the volume is higher than the external pressure by the amount, the change in pressure, fluid will jet from the hole with velocity v. So with this, think about a ventilation hole being cut in a house. We have that box that's burning, that compartment, that room that's burning inside the house, and that pressure is building up because the temperature is increasing, that volume of gas, the pressure is increasing in that volume. As you cut a hole in the roof, we punch through the ceiling. What do we see? We see that column of smoke begin to rise out because the pressure is greater inside. Pressures want to flow from a high to a low direction. So we see that smoke move from outside the room, the superheated gases from outside that room to the external part of the house. And that's what we're trying to accomplish when we have an offensive ventilation heat hole. Just moving through some of these things. Viscosity. This is the force needed to overcome frictional resistance offered by a fluid. So a drag force slows fluid flow when it flows over an immersed object. So friction, as water's flowing through a hose, there's friction depending on the size of the hose. The smaller the hose, the more friction there's going to be. The larger the hose, the less friction there's going to be. Viscosity, though, deals with how well it moves over that thing. We see that some items are more viscous than others. You know, you look at water and oil, they flow differently based on how they flow over those items. As we talk about like a fluid flow, we talk about a boundary layer. This boundary layer is a slow-moving region of the fluid at the perimeter of the moving fluid. So think about like a cloud of smoke as it's moving over a item. That smoke near the surface of it is much thicker. That boundary layer is right there, and it's slower to move than that smoke is away from that solid. Fluid flows can be either laminar or turbulent in fashion. Again, I'm going to use smoke kind of to give you the idea. Turbulent smoke is very nasty, very ugly, dark smoke with lots of action. It's got a lot of movement. It's stirring. It's not real smooth. When we talk about laminar smoke, it's more that light smoke. It's smooth flowing, things like that. It's kind of the difference between laminar, where it's not as much pressure. We can tell that our fire is not as big. There's not as much heat versus that turbulent smoke that's just that dark, angry, black smoke where you know you got a good ripping fire underneath. Viscosity, page 53 defines viscosity as a property of the fluid that gives rise to this friction is its viscosity. Viscosity is important in fluid flows for three reasons. When a fluid flows over an immersed object or through a duct, a drag force slows the fluid down. Talked about the boundary layer, and then we talked about the fluid being either laminar or turbulent as well. The viscosity of a fluid varies with temperature, but is only slightly dependent on pressure. So warming a liquid decreases the viscosity. Warming a gas increases the viscosity. So think about oil. As we warm it, the viscosity is decreased. So as we cool it, the viscosity is much slower. With a gas, it's the inverse. So warming a gas increases the viscosity. Cooling a gas is going to decrease the viscosity. Laminar and turbulent flows. To look at laminar flows, we're on page 55. You see on figure 4-1, and right here's that figure, the laminar flow. You know, it's much more see the blue and red ink being mixed together, creating that more turbulent type of a flow. So there's a couple of ways to accomplish a turbulent flow. Decrease the fluid viscosity, increase the diameter of the pipe, so those objects are going to move around. They're not going to hold their shape as much. Increase the roughness of the inner wall, and increase any pressure fluctuation in the flow. You can also generate turbulence by having the laminar flow go around an object. So here we see a laminar flow, goes around an object, and then turbulent profile afterwards. So we talk about buoyancy, and this was came through. It was thought up, or not thought up, but discovered by Archimedes in 212 BC, which basically said any object wholly or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced. For example, hot air rising, light objects floating in water. That's dealing with buoyancy. This applies to a fire's hot plume and how it spreads. So the density of the fire gases is less than the ambient air around. So because the ideal gas law, at a constant pressure density inversely proportional to the absolute temperature, so because those fire gases, the density is less than the ambient air around them, they start to rise, they go up. The buoyant upward force is proportional to the difference in the densities of the two flows. So how much that is going to rise and how much fast it's going to go up is based on the difference between the density of the smoke and the density of the ambient air around it. So that's where we find that the upper part of a fire room is usually much hotter than the lower portions. So if a fire plume is narrow or the heated region is small, the upward flow is laminar. We see wider plumes that are more turbulent, and the turbulent plume entrains or it draws in the surrounding air more rapidly. A major influence on fire-generated flows is the temperature, the speed of the velocity of that heat movement, those gas movements, and then also the smoke concentration. So all three of those things are going to have a major influence on the fire-generated flows. So in summary, we looked at Newton's 3 laws of motion, Newton's laws of gravitation. Talked about potential energy being energy that is stored waiting to be used. Kinetic energy is energy in motion. There's some simple equations to express the relationships between different things, but again, we're not worried about calculations. Airflow in fires can be either laminar or turbulent. Remember that laminar is that light, wispy, more uniform type of a flow, and that turbulent is that dark, angry, just lots of movement, lots of things happening in there. Viscosity and buoyancy also play key roles in these fire flows. Viscous effects play a role in water flow through pipes and hoses as well. So as we move back to chapter 4, page 49, again, we talked about at any given time, this is under the momentum and acceleration of a rigid object, second sentence, at any given time, an object has momentum equal to mv, where m is the mass of the object and v is its velocity. Page 51, you're going to want to know and understand potential energy and kinetic energy. Page 52, right-hand column, middle paragraph there, second sentence, it says, the gravitational pull on the column squeezes the water near the bottom of the column. As a result, the pressure within the water is higher at the bottom and decreases with its increasing height. Think of that straw, the gravitational pull on the column. So know and understand that paragraph. On the right-hand column of page 53, know and understand viscosity. On page 54, you're going to want to know and understand the turbulent flow. Page 56, in those bullet points there, the second one, increase the diameter of the pipe. What is that in regards to? That is in regards to 4 ways to have a laminar flow transition to a turbulent flow, is increasing the diameter of the pipe. And then on page 57, there's going to be 3 things that you're going to want to know and understand from there. Buoyancy, that's right under buoyancy, know and understand that definition. Then the first line of the second paragraph there, this principle applies directly to the hot plume that rises from a fire and then spreads elsewhere in the fire room and into adjacent spaces. And then the first sentence, or 2 sentences of the last paragraph, it says, in fire plumes where the heated region is small and the plume narrow, such as the region over a candle or smoldering cigarette, the upward flow will be laminar. So we have that small flame, that small amount of smoke given off, that flow is laminar. When we see wider plumes, they're more likely to be turbulent than narrow plumes. If the heated region is as wide as 1/2 meter, so about 1.5 feet, or actually, yeah, the upward flow will be turbulent. So chapters 3